Welcome to today's Explainer. Let's jump right in. I want you to imagine your body as this bustling, infinitely complex city, complete with a vast network of highways and roads. Well, in this world, platelets are your highly specialized rapid response emergency repair crew. When there's a structural failure, like a tear in a blood vessel, these microscopic fragments are literally the first ones on the scene to prevent a catastrophic leak. Today, we're going to decode exactly how they're made, how they work, and why, honestly, you couldn't survive without them. Here is our agenda for today. We're going to meet the repair crew, step inside the giant platelet factory, look at the anatomy of a responder, unpack their tool belt of granules, walk through their 3-stage 911 protocol, and finally, look at the real-world health risks.
Section 1. Meet the repair crew, decoding the science.
Let's start with the medical terminology, which actually tells us exactly what's going on. Thrombopoiesis. It sounds complicated, but it literally translates to clot making. You've got thrombo for clot and poiesis for making. That single word perfectly captures the ongoing dynamic process of your body manufacturing these vital little responders. Now, what about the word megakaryocyte? This breaks down into mega for huge, karyo for nucleus, and cyte for cell. It's a giant platelet-making cell. But here's the wild part, and I really want to emphasize this. Platelets themselves are not actually cells. Nope, they don't even have a nucleus. They're just tiny, incredibly complex fragments that physically break off from this massive parent structure, the megakaryocyte.
Section 2. The giant platelet factory inside the bone marrow.
To really give you a sense of scale here, the megakaryocyte is an absolute behemoth. It measures somewhere between 50 to 100 micrometers across. Now, in the microscopic world of human biology, that is staggering. It is the single largest cell you'll find anywhere in your bone marrow, just sitting there like this massive manufacturing plant surrounded by tiny little workers.
And what's truly mind-blowing is the sheer scale of production happening inside that factory. The megakaryocyte has this single, huge, multi-lobed nucleus. Now, a normal human cell holds just 2 sets of DNA, right? Well, this absolute unit holds anywhere from 16 to 32 sets of DNA. Because of that massive genetic payload, a single megakaryocyte acts like an industrial assembly line, churning out an astonishing 1,000 to 5,000 individual platelets before it's finally spent.
So how does a regular cell turn into this massive factory? It's a 6-step assembly line, all overseen by a critical factory manager, the hormone thrombopoietin, or TPO, which comes from your liver. It starts out as a small megakaryoblast. Then, in step 2, as a promegakaryocyte, it does something amazing. It copies its DNA over and over again without actually dividing. That leads to step 3, the massive cell packed with DNA. Next, it stretches its cytoplasm into these long extensions called proplatelets that reach right into the blood vessels or sinuses of the bone marrow. Finally, the rushing blood literally shatters those extensions into the tiny circulating fragments we call platelets.
Section 3. Anatomy of a responder, scale and structure.
If we took a sample of your blood right now, your normal circulating platelet count should be between 150 to 400 times 10 to the 9th per liter. It's a massive fleet. But they live fast and die young. They only have a lifespan of about 7 to 10 days, meaning roughly 10% of your entire platelet fleet has to be replaced every single day. Oh, and here's a super cool fact. About 1/3 of your body's total platelets aren't even circulating. They're just sitting on standby, stored safely inside your spleen, waiting to be deployed if a major trauma happens. Now, even though they aren't true cells, each platelet is incredibly complex. They're highly organized into 4 distinct structural zones. First, you've got the peripheral zone. That's the outer membrane loaded with essential receptors like GPIB and GPIB/3A. Second, the sol-gel zone, which has microtubules and actin that provide the literal muscle for changing shape. Third, the organelle zone. Think of this as the cargo bay, holding mitochondria and the all-important granules. And finally, the membrane system, featuring a specialized open canaculary and dense tubular network. This intricate internal plumbing allows the platelet to rapidly dump its stored chemicals during an emergency, without having to wait for normal cellular diffusion. To really visualize the genius of this design, you have to picture their physical transformation. On a normal day, cruising through your bloodstream, they maintain a peaceful, resting disc shape. Small, aerodynamic, perfectly designed for smooth, uninterrupted travel. But the absolute second they sense chemical signals of vessel damage, boom, they use that sol-gel actin to instantly mutate into an activated, aggressive, spiky shape. They spread way out,
vastly increasing their surface area, reaching out with these spiky little arms to grab onto the damaged wall and lock onto other platelets.
Section 4. Granules and the tool belt. Chemical warfare.
A repair crew is only as good as its tools. Inside that organelle zone, there's a strict division of labor between two types of granules. First, we have the dense granules. These look darker under a microscope, and there are only a few of them, maybe 3 to 8 per platelet. They contain things like ADP, ATP, calcium, and serotonin. Their job? They are the chemical sirens. Upon activation, they release these chemicals to recruit more platelets to the scene. On the flip side, you've got alpha granules. These are lighter but way more numerous, about 50 to 80 per platelet. These are the cargo carriers that hold the physical building blocks, unpacking proteins like fibrinogen, von Willebrand factor, and factor V to actually construct and secure the physical barricade of the clot. Section 5. The 3 stages of repair, the 911 protocol.
This brings us to the ultimate survival protocol, the rule of 3. The moment there is a tear, stage 1 is adhesion. They stick specifically to the damaged blood vessel wall using von Willebrand factor and their GPIB receptors. Stage 2 is activation. They undergo that dramatic change into the spiky shape and release their granules, spewing ADP and thromboxane A2 to call for backup. Finally, stage 3 is aggregation. The backup arrives and they stick to each other. They literally lock hands using their GPIB/IVIA receptors connected by sturdy fibrinogen bridges to form a solid, watertight plug. So remember that: adhesion, activation, aggregation.
Section 6. Health risks and review. Real-world stakes.
Remember that normal count range we talked about earlier? Maintaining that delicate balance is absolutely critical for your survival. If you have thrombocytopenia, which is a low count, dropping under 50 means you'll bruise incredibly easily. If you drop under 20, your emergency repair crew is so dangerously understaffed that you risk spontaneous, life-threatening internal bleeding without even taking a hit. On the other extreme, if you have thrombocytosis, where your count explodes to over 1,000, your body is wildly overpopulated with repair units. That creates a severe risk of massive, unwanted blood clots that can completely block off healthy arteries.
This delicate balance explains exactly why a common over-the-counter medication like aspirin does what it does. Aspirin specifically blocks the daily function of these repair cells. It intentionally hinders their ability to aggregate, artificially keeping the crew offline just enough to prevent unwanted blood clots that cause heart attacks. But on the darker side, certain illnesses can completely hijack this system. Dengue fever actively decimates your platelet population. Immune thrombocytopenia, or ITP, causes your own immune system to mistakenly destroy them. And DIC rapidly, dangerously consumes your entire fleet of platelets all at once.
Before we wrap up this explainer, I want you to burn this takeaway summary into your memory. Number 1, never forget that platelets are mere fragments of giant megakaryocytes, not true cells themselves. Number 2, their production is strictly governed by the hormone TPO from your liver. Number 3, they live fast and die young within 7 to 10 days, hovering in that critical normal range of 150 to 400. And number 4, their sole dedication in life is the rule of 3, adhering, activating, and aggregating to save you from bleeding out.
To make sure these concepts have truly locked in, I highly encourage you to pause the screen right now. Use these 3 self-check questions to test your active recall. Can you define the megakaryocyte and remember its staggering output? Do you remember the division of labor between the chemical sirens and dense granules versus the structural proteins in alpha granules? And can you name the specific membrane receptors used for adhesion and aggregation? Give it a try.
As we finish up, reflecting on everything we've covered leaves us with a truly fascinating biological mystery. Think about it. If these tiny fragments are just pieces of cellular debris that don't even possess a nucleus, DNA, or a brain of their own, isn't it absolutely incredible how perfectly their built-in chemical programming tells them exactly when, where, and how to instantly sacrifice themselves to save your life? It is a marvel of evolutionary engineering playing out in your veins every second of every day. Thanks for joining me on this explainer, and keep questioning the incredible mechanisms hiding just beneath your skin.